Okay, man, that really got things stirred up there, didn't it? Okay, our next presentation is by William Van Beesen on maximizing CCSDS protocol performance.
Yes, it's green now? Okay. So it's been about, is it too loud? Okay. It's been 10 years now since I attended my first flight software workshop when it was held at APL 2008. I think I was an intern at the time working with Chris Krupiarts, who's the founder of this whole thing. He's not here this year. So it's been an interesting 10 years. I've probably come back 5 years since then. Back then, it was all just Goddard and APL and some JPL, and now it's exciting to see how it's grown and the diversity of organizations that are here now, especially a lot of small businesses. So it's been a really neat development. I hope that trend continues. So I used to work at APL for a long time. I've since left, and I work at a new organization now called Gigantum. We're a very small company dedicated to scientific reproducibility, and the product that we're putting together is intended to help researchers do higher quality science. So 2 years ago at the Flight Software Workshop, when it was held in Pasadena, I presented this piece called Maximizing Data Return for the Europa Lander, a trade study in the application of CCSDS protocols. It was published, the full manuscript was published a few months later at the 2017 Aerospace Conference. And this was a pretty wide-ranging trade study that covered all aspects of telecommunication, all aspects of the telecommunication subsystem. It looked at implementing a full DTN protocol stack and went all the way down to the RF level. It considered some of the, I guess, challenges that are unique to the Jupiter environment. And so the rest of this talk, which is going to focus in reproducing some of the key results of this paper. I'm not going to talk too much about the challenges of working around the Jupiter environment, because I think that's a little bit out of scope. But nonetheless, I'll take just a minute. So the concept behind this paper was for a lander to Europa. And this mission was due to follow the Europa Clipper mission, which I think is going to launch in the year 2022. So the idea was that this lander would follow the Clipper, launching a few years afterwards, land on the surface of Europa, possibly use the Clipper as a data relay. The lander would be powered by a battery with a lifetime of about 20 days, and in those 20 days, it would collect as much data as it could and downlink as much as it could. So what I'm presenting today and the work I've done since then, I worked with a few graduate students in the data science department at GW, and we went about trying to reproduce some of the key claims made in this paper. I'll talk about what those are next. So the objectives in the research I did for this is to independently validate and reproduce some of the key claims in the original publication that had to do with networking and RF efficiency. So specifically, the intention is to produce some kind of data artifact that contains the code, the data, and the graphs for any of you, any interested members of the community, to, in a snap of your fingers, recreate, validate, and then iterate on these results. So you can check that our research methods were sound, that our results are sound, and that if there's any other compelling research questions, you can quickly address those and develop that further. So this data product, I'm going to have a link at the end of this talk. It's published as a zip file. You can use our product, our Gigantum product, to open it, but our commitment is to open source and open data, so we don't lock anyone into our system. It's otherwise just a zip file that contains code and data, as well as a Docker image and Docker file to reproduce the computing environment. So it'll be available for anyone as soon as this talk is over to start reproducing and validating. And then just a brief note, although I worked at APL, this doesn't contain any information that I had while at APL. All material for this comes only from the publication and any related CCSDS documentation. So I'm realizing this presentation is geared for those who've worked in space networking and are familiar with DTN, CFDP, and the related protocol suite. So if if that's not your field, I apologize if this is a little too specific. So in the paper and in our reproduction, we broke it down into about 2 key phases. The first looked at link efficiency at the network and data link layer. The next looked a little bit deeper at the RF level trade-offs that could be made. So the 3 key claims we validate in the first phase is that link efficiency, and I'll define that in the next slide, is maximized when Prox1 frame size is maximized, Prox1 being the proximity 1 data link layer service. CFDP PDU segment length is a key metric of link efficiency, CFDP being the file transfer protocol defined in the CCSDS standards. And the third is that CFDP can sustain decent efficiency even in relatively high loss scenarios, so even when the bit error rates creeps into 1 in the thousands. Moving on to the RF level trade-offs that could be made, one of the key claims was that there was some kind of inverse relationship between energy consumption and data return, meaning that if you wanted to minimize the amount of energy needed to downlink a file, you had to accept a higher time needed to downlink that file. The flip side being that if you wanted to get a certain amount of data down fastest, it would cost you with more energy. And in the paper, it formalizes that, and we reproduce that here. The second key claim, and I thought this was particularly interesting, is that there's an inflection point beyond which increasing link performance decreases battery lifetime, meaning that there's a point beyond, let's measure it by a certain bit error rate, where if you devote resources to improving the performance of the link, not only do you get diminishing returns, but you actually get negative returns, and there's some kind of benefit for throttling that back and accepting a higher dropped frame rate or bit rate, basically. So this is a method for phase 1. So I created a new project, a new Gigantum project, which under the hood assembles a Docker image with Python, Jupyter, and the Jupyter here is not the planet, it's the interactive Python notebook. And I'm just actually curious, how many of you have used Jupyter and Python for any kind of data science? Okay, all right, cool. So all the work here is presented as Jupyter notebooks. So within this project, in this Docker image, I developed what I call a medium fidelity CFDP and Prox1 network stack. It's not high fidelity because it's not a fully compliant CFDP implementation or anything like that, but nonetheless, it is the implementation of a protocol stack that takes a data file, chops it up into bits, puts those bits into packets, puts those packets into frames, puts it through a network simulator that drops the frames according to some probability distribution, reassembles them, prompts for retransmissions, does all the stuff that a file transfer protocol would otherwise do. And then what I did was I took the simulator and I ran it over a range of packet sizes, frame sizes, and bit error rates. And what I was able to do is to make a sort of surface plot that would show the link efficiency as a function of this bit error rate and packet sizes. And from the peak of that curve, so to speak, you can see what configuration makes that link most efficient. And then I've been talking about link efficiency, and the definition is here. It's just the ratio of bits in a data file to the bits transmitted. And so in a perfect link where there would be no bit errors, the efficiency would be pretty close to 100%. It wouldn't quite be 100% because there's going to be some packet headers and sequence patterns and trailers and things like that. And then the efficiency would go down dramatically as bit error rate goes up because there'd be more and more retransmissions. So here's the first set of results. On the left are the results from the original publication. On the right, let's see, there we go, are the results from the reproduction. So I'll just speak a minute about each of these. And again, as soon as this talk is done, any of you can fire this up and play with some of the parameters and see how they check out. So the top two consider a link where there was pretty much no bit errors. And so this is a plot of efficiency as a function of packet size on this axis and frame size on this axis. And so I think in general, the results check out pretty well in that there's a peak at each corner here, which corresponds to a large frame size and large packet size, and then decreases as you go across here to where you're getting small packets and small frames, which it's kind of intuitive because there's going to be more overhead relative to data payload over here. I'm not too concerned about this kind of dramatic trail off here because that's modeling when prox1 frame sizes are close to 0 bytes, which isn't a realistic scenario in any case. But the trend here, they seem to match pretty well. It gets a little bit more interesting at the bottom, which considers a much higher bit error rate. And it's not an apples-to-apples comparison because the original publication was parameterized with frame error rate. My simulation over here used bit error rate. And what's being compared here is actually, even though they're lossy lengths, this one is far lossier than this one. But in general, the trends also seem to check out in that there's a peak efficiency kind of in the back corner, which correspond to smaller packets, and then it becomes dramatically less efficient as the packet size increases. So this was a compelling result as we wrapped up the first phase of the study. And then the scales are a little bit different. I think this one only goes down to 40%. This one goes down to 0. So in the second phase, we dug a little bit deeper and we looked at some of the RF trade-offs that could be made. So to do this part, I reused my simulator from the first phase that did simulated file exchanges over the CFDP prox1 networking stack. And I ran it again over a range of bit error rates, ranging from 1 in 10 to the third, which is 1 in 1,000 bits in error, to 1 in 10 to the eighth, which I think is 1 in a million or 1 in 10 million or something like that. And I used that to estimate the energy consumption for that given transaction. And to do that, I used this graph on the right. What this graph on the right shows is the relationship between bit error rate and energy per bit. I think it's technically received energy per bit, but we assume that it corresponds pretty well to the transmitted energy per bit. And it's in log-log scale, and the intuition is that as you reduce the error rate, your transmitted energy per bit goes up, which is intuitive. You have, I guess, a louder and more clear signal, so the error rate goes down. And then the flip side being, as you scale back the energy per bit, you accept a much higher bit error rate. So, 1 in 10 squared is 1 in 100 bits in error, 1 in 1,000 bits in error. And this whole graph can be a bit overwhelming, but for our purposes, we actually only consider this solid blue line that pertains to a certain coding rate and frame size and things like that. And this is the only one under consideration. So from my simulator in the first phase, that got me a metric of efficiency. And then it's a simple expression to estimate the amount of bits transmitted. And then when you get the amount of bits transmitted, you can multiply it by, given some frame error rate, by the EBNO down here. And then you can estimate what is the cumulative energy for that transaction. And our goal here was to understand this interrelationship between link efficiency, bit rate, and energy consumption. So these are the results. Again, the results from the original are on the left. From our reproduction, this is the graph on the right. Before getting into how they compare, I'll give a little bit of an elaboration on what's going on here. It shows the energy consumed for a given downlink as a function of the energy per bit, and then it also shows a downlink in red. And what it shows is that there does seem to be some kind of trade-off, that if you want to get data down faster, you have to accept a higher energy consumption. And the flip side is if you want to save on energy, it's going to cost you with a higher downlink duration. But one thing that's really surprising going on here is that as you move to the right, the bit error rate is going down. So there's actually a lot fewer errors and a lot fewer packets being retransmitted. And the really striking thing here is that even though there's so many packets being dropped here and retransmitted, it nonetheless consumes less energy than if you're operating on a much more perfect channel where there's much fewer frames and packets being dropped and retransmitted. So that was pretty surprising. And then, so now moving on to our reproduction on the right, I think it's a little bit more granular, and the results are a little bit more high resolution than what's going on here, which I think basically just sampled it 3 places. And what this shows is, I think, a little bit more nuanced of a picture than what's going on the left. It shows that, again, as you increase the energy per bit and have a lower error rate, the amount of energy consumed goes up. And as you go to the left, it also goes up because what's happening here is that at a bit error rate of 1/10⁻³ pretty much all the packets are being dropped, and it's a marvel that, you know, any communication could be done at all. So the amount of energy, even though it's a small amount of energy per bit, it's nonetheless eating up so much. But I think that's not really a realistic scenario. That would be that the RF system would calibrate or the RF system would be set to a bit error rate of 1/10⁻³. One thing we could not reproduce was this kind of inverse relationship between the downlink duration and the energy consumed. And in fact, the energy consumed is this kind of transparent line on the right. It seems to show that they're actually fairly well correlated, I guess. But it occurred to me a few days ago, actually, that what I was not accounting for here is the latency or the round-trip light time. So accounting for that, this picture might change dramatically and match this, and that'll be something for some further research, I think. I'd be curious to see how that turns out. So to wrap it all up, in phase 1, I think the reproduction, it matched the claims from phase 1 fairly well. And the data suggests the 3 initial claims probably pretty good. In the second phase, I think the picture got a little bit more complicated, and I think that's due to the nature of the second part and looking into the RF system itself just being a little bit more complicated. We showed that there is some point beyond which devoting more resources to improving link quality actually costs you more than it's worth. But we weren't able to reproduce the result of that inverse relationship between energy consumed and downlink duration. But again, it occurred to me that I think there was a flaw in my second phase where in my metric for computing that. So that's it. I have some ideas for further work. I would love to have this thread of research continue, and maybe if there's some student here who for next year would like some work to do, it'd be interesting to continue this and see if they can get higher quality results, more refined results. Some ideas would be observing the energy trade-off for other rates and other data encodings that pertain to other lines along that Ebno curve that I showed a few slides ago. I think it would also be interesting to more accurately model the bit errors that would occur in a Jovian environment. So in my simulation, I parameterized it with the bit error rate that it inserts the bit errors according to some uniform distribution. But I think it's more likely that errors would cluster together. So if we could alter that probability distribution, it might be a better modeling of what will happen around Jupiter. And then finally, I think it'll be neat to put in a real CFDP engine. I think it's open source, and it would be neat to actually put that in the loop rather than relying on my medium fidelity simulator. So the Docker image, the code, the Jupyter notebook, everything needed to reproduce this result, everything needed to reproduce the data and code that generated each of those charts is available. It should be up right now. You can get the zip file from my GitHub page. You can otherwise check out the official Gigantum project from here. So before I wrap up, we're Gigantum. We're a very small organization, just about 5 people. We're dedicated to open source, and the product we're putting together is a system for collaborative, reproducible science. So we have corporate and federal sponsors that are interested in our work because they need, when they charter research and put out contracts for research, they don't just need a manuscript. They need a data product that is reproducible and able to be handed off to other groups for further work. And so we work with journals as well, because there's a bit of a crisis, particularly in data-intensive computing in the machine learning world, of reproduction. And so we're out there to solve that problem, and our contact information is here. And with that, I'm all finished, and I'll take any questions. Yes?
Yeah. Did you say that you have the CFDP, like a library or a client or a network stack that is open source?
I think, is there anyone here that's at Goddard that is part of the...
Is it IonLib?
Is it? No, the CF app is available in the CFS. Okay.
Oh, it's that one? Okay. I thought...
Okay.
If it's another one, I'd really, really like to know.
I am afraid I'm going to disappoint you so much because my medium fidelity simulation is in here in this project, but it's not a compliant CFDP implementation. It just kind of approximates a TCP or FTP-like protocol. So I hate to disappoint you.
Could you go back to the crisscross red and blue line slide?
Yep. Are you an RF engineer by any chance?
Not even close.
Okay, good.
Several times you use the term lower bit error rate.
Sure.
And you also use the term higher power.
Yeah.
Why are those the same?
I'm not an RF systems engineer, and that's why I asked.
The point
you.
is that was kind of a conflation.
The intuition is that with a higher energy per bit, it's presumably on a more loud and clear channel.
I agree.
Uh-huh.
Now, why is the converse true? Couldn't that be according to your conditions?
State the claim again. Maybe I didn't process
No, I agree.
Uh-huh.
Presumably, under the same conditions, higher power gets you a lower bit error rate.
Mm-hmm.
But is that the only way to get a lower bit error rate?
No, it's not.
That was the confusion, it sounded like. There's a conflation of terms there. That could help explain your results.
Okay.
Any other questions?